Hi, my curious friend. Welcome to my channel. Have you ever wondered what would happen if gravity, the greatest invisible architect of our beautiful universe, suddenly working now? This is exactly we are going to investigate today's science story. You know, it's one of those quiet, ordinary moments. You're holding your morning cup of coffee, and you go to place it back on the desk. But this time, your hand lets go, and the cup just doesn't get the memo. It doesn't fall. It just hovers there, right where you left it. A perfect porcelain satellite orbiting, well, you. The hot brown liquid inside slowly detaches, forming wobbling amorphous blobs that drift out like lazy jellyfish. You stare, your brain refusing to process what it's seeing. And then you feel it. A lightness, a weird, unshackling sensation in your feet. You push off the floor, just a little, experimentally, and you don't come down. What you've just experienced in this impossible quiet chaos is a universe that has just lost one of its most fundamental rules. Gravity has stopped working. Now I know what you're thinking. Everything would just float away. And you're right. But my friend, that is just the very, very beginning of the story. That's the title of the book. What we're about to do is read every single page, from the first bewildering second to the final cold, dark ending of everything. So, get comfortable. Let's talk about what happens when the universe's most reliable anchor simply lets go. First things first, let's be clear about what we're switching off. We're not just turning off Earth's gravity. That would be strange enough. No, we're turning off the force of gravity itself, everywhere, all at once. The fundamental force described by Newton and Einstein, the curvature in space-time that attracts objects with mass towards one another. It's not just Earth letting go of you, it's you letting go of Earth. It's the sun letting go of the Earth. It's every atom in your body letting go of every other atom. It is quite literally the glue of the cosmos deciding to take an indefinite and cataclysmic vacation. So, let's start small, right here, right now, with you and your suddenly flight-worthy coffee cup. The initial moment would be one of profound and utter confusion. Our brains are hardwired for gravity. Our inner ear, a beautiful little fluid-filled gyroscope, is constantly telling us which way is down. The pressure on the soles of your feet, the weight of your arms, the very way our bodies are built, it's all predicated on a constant, unyielding 9.8 meters per second squared pull towards the planet's center. The moment that pulls vanishes, that internal compass doesn't just spin, it shatters. The fluid in your inner ear would now be weightless, sloshing around without a preferred direction. Your brain would receive signals of frantic, tumbling motion, even if you were perfectly still. The immediate, overwhelming sensation for almost every single human being would be a violent, uncontrollable vertigo and nausea. It would be 1 billion times worse than the spin cycle on a washing machine, because there would be no right way up to orient yourself. Your vision might swim, your stomach would lurch, and the primal part of your brain would scream that you are in mortal, free-falling danger. But you aren't falling. There is no down to fall towards. Look at your hands. They feel strange, don't they? Lighter. Your arms, which you normally have to consciously hold down or rest on something, would naturally float into a more neutral position. If you were sitting in a chair, you'd no longer be pressed into the seat. You'd be lightly resting on it, held there only by the faintest of molecular adhesions. A deep breath, a slight shift, and you'd begin to drift upwards, your back peeling away from the chair's fabric. If you were standing, your body's natural slight sway normally corrected by gravity, would now become a drifting motion. A tiny push from your toes against the floor would send you gliding slowly towards the ceiling. Now, let's look around the room. Everything not nailed down is about to become a projectile, but not a fast one. That's the first interesting quirk. In the movies, when gravity fails, things instantly zip around at high speed. That's not quite right. Objects have inertia. They like to stay still if they are still, or keep moving if they're moving. The coffee cup you released simply stayed where it was because no force was acting on it. It wasn't being pulled down anymore. But the air in the room is still there. So, as you move, you create tiny air currents. That coffee cup might begin a slow, graceful drift towards an air vent. Your pen on the desk might start to rotate lazily. But then there are the things that were under tension or pressure. That's where the immediate danger lies. Think about the lamp on your desk, plugged into the wall. Its cord was dangling down. Now, with no down, the internal springiness of that coiled cord might cause it to retract slightly, pulling the lamp into a slow, tumbling motion. Not so bad. But now think bigger. Your bookshelf. All those books were pressing down on the shelves. The shelf itself was being compressed by the weight. The moment gravity stops, that compression is released. The wood of the shelf, if it's slightly flexible, might actually bow upwards a tiny bit, springing back like a released diving board. This could be enough to send the entire row of books floating off it in a slow-motion cloud of paper and hardcovers. The real chaos, however, is happening in your walls and under your feet. Your house, your apartment building, every structure ever built by humans was designed with one primary, constant enemy in mind: gravity. It fights gravity every second of every day. The walls are in compression, holding up the weight of the floors and roof above. The foundations are under immense pressure, bearing the load of the entire structure. Take away gravity, and you take away the very thing these structures are fighting against. It's like two sumo wrestlers locked in a stalemate, pushing against each other with all their might. And then one of them suddenly vanishes. The other goes flying. The release of this stored compressive energy would be catastrophic, but again, not necessarily explosive in the fiery sense. It would be a slow, groaning, terrifying unwinding. Concrete, which is incredibly strong under compression, but weak under tension, would begin to crack and spall as its internal stresses redistributed. Steel reinforcement bars, now free of the load they were bearing, would flex. The entire building would emit sounds you've never heard before, deep, resonant groans and sharp, percussive cracks as decades of accumulated strain were released in a matter of seconds. Windows would be a major point of failure. The pane of glass in your window is held in by a frame. It was being pulled down by gravity, putting pressure on the bottom of the frame. Now that pressure is gone. The seals and the frame itself, designed to hold the glass in against a downward pull, might now be the only thing holding it in at all. A slight pressure difference between inside and outside, or a vibration from the building's groaning, could be enough to pop entire panes of glass out of their frames. They wouldn't shatter immediately. They'd just drift away, large, transparent, and deadly sheets of glass. And what's outside? The air, the atmosphere. Now we're getting to the planetary scale events. But let's not get ahead of ourselves. We're still inside, dealing with the floating, nauseous you. You've managed to push off from the ceiling and are now drifting in the middle of your living room, a slow-motion astronaut in a world gone mad. You're surrounded by a constellation of your former life. books, pens, photo frames, a television remote, all doing a silent, weightless dance. You need to get your bearings. You try to swim like you would in a pool. It sort of works, but it's inefficient. You flail, creating chaotic vortices in the air, which mostly just make you spin. You discover Newton's third law the hard way. For every action, there is an equal and opposite reaction. If you wave your arm hard to the right, your body spins to the left. To move effectively, you learn you need to push off a solid object. You aim for a doorframe, kick off the wall, and glide down the hallway. It's starting to feel almost peaceful. The initial vertigo is subsiding, replaced by a sense of surreal wonder. Then you drift into the kitchen. The kitchen is a whole new level of danger. Remember the refrigerator? It's a heavy box, but now weightless. It's still massive, though. Mass and weight are different. Your weight is the force gravity exerts on your mass. Without gravity, you have no weight, but you retain all your mass, and thus all your inertia. A massive object is still hard to get moving, and once moving, hard to stop. The refrigerator is no longer anchored by its weight. It's sitting on the floor, but the friction that was holding it in place is now gone. Friction depends on the normal force, the force pressing the surfaces together, which was provided by gravity. No gravity, no normal force, no friction. That fridge is now a free-floating several 100-kilogram monolith. If it was on an uneven floor, or if the house shifts, it could begin to drift. Bumping into it would be like bumping into a drifting freight train. It would barely notice, and you would go spinning away, possibly with broken bones. And inside that fridge, the stuff that was sitting on the shelves is now floating. The milk carton, the jar of pickles, the leftover spaghetti. The door, which you might have closed loosely, could slowly swing open, releasing this cloud of food into your kitchen. But that's the least of your worries. What about the gas stove? If it was on, the flame would be behaving very strangely. On Earth, the hot combustion gases rise because they are less dense than the surrounding air. That's convection, driven by gravity. Without gravity, there is no up for the hot air to rise. The flame would become a dim blue spherical ball, suffocating in its own waste products because there's no buoyancy to draw in fresh, oxygen-rich air. It would likely go out quickly, but if the gas was still flowing, you'd now have an invisible, expanding cloud of highly flammable gas filling your kitchen. One spark from a floating, jostling appliance and, well, you can imagine. The water in the pipes is another issue. Your home's plumbing relies on pressure, which, in municipal systems, often comes from gravity. Water towers are placed high to create pressure for the homes below. Without gravity, that pressure head vanishes instantly. The water flow to your taps would stop immediately. But the water that's already in the pipes is now weightless. It's not being pulled down towards the drains anymore. If you open a tap, you might get a weird, sputtering blob of water floating out. But the system is effectively dead. More critically, the water in the U-bend of your sink's drain, the trap that keeps sewer smells out, is now free to float away. Soon, every drain in your house becomes an open pipe to the sewers, allowing gases to freely diffuse into your home. But you don't have time to worry about the smell. A low, deep rumble begins to vibrate through the very structure of the building. It's not a sound you hear with your ears as much as you feel it in your bones. It's the sound of the world itself coming undone. It's time to look outside. You maneuver to a window, or where a window used to be, and peer out into the world. The scene is one of silent, breathtaking, and horrifying grandeur. It is not the explosive, fiery chaos of an action movie. It is slower, more graceful, and infinitely more terrifying because of its scale. First, the sky. It's not blue anymore. It's black. A deep, star-flecked blackness. Where did the blue go? The blue sky we know and love is caused by Rayleigh scattering, sunlight bouncing off the molecules in our atmosphere. But that atmosphere, that blanket of air, is held in place by Earth's gravity. The moment gravity vanishes, it is no longer held. The entire atmosphere of Earth begins to expand outwards into the vacuum of space. It doesn't happen with a whoosh. It's not like a balloon popping. The air molecules are all moving at incredible speeds, hundreds of meters per second, in random directions due to their thermal energy. Previously, gravity pulled them back. Now, nothing is pulling them back. The molecules in the upper atmosphere, already the most energetic and tenuous, are the first to go, streaming away into space almost instantly. But even at ground level, the air is beginning to thin. The blue sky vanishes because the dense layer of air that scatters blue light is rapidly dissipating. You are, effectively, standing on the surface of a spacecraft that has suddenly lost its hull. The air pressure is dropping. Fast. You feel it in your ears, a sudden, painful pop that doesn't resolve. It's the same sensation as a plane ascending rapidly, but 1,000 times more intense. This is decompression sickness on a planetary scale, the bends for the entire world. The nitrogen dissolved in your bloodstream is beginning to form bubbles. It's excruciating. Your vision starts to tunnel. This is one of the first global killers. Within minutes, anyone not in a pressurized suit or environment will lose consciousness from hypoxia, lack of oxygen, and suffer fatal embolisms as their blood literally fizzes like a freshly opened soda. But let's assume, for the sake of our story, that you are miraculously protected in some kind of pressurized bubble. What do you see? You see the end of the world in slow motion. The ground itself is breaking apart. Remember the compressive forces in your house? Multiply that by 1 billion. The Earth is a massive ball of rock that is under unimaginable pressure from its own weight. The core, the mantle, the crust, all of it is being squeezed by the gravitational pull of all the material above it. Take away that squeeze, and the planet's very substance, from the core to the mountaintops, experiences a catastrophic release of pressure. The solid crust of the Earth is not a single, unbroken eggshell. It's a jigsaw puzzle of tectonic plates. These plates are jammed together, sliding under or past one another, their motion driven by the slow convective churn of the mantle below. The forces locking them in place, friction and pressure, are immense. The release of gravitational compression would act like taking the lid off a pot of boiling thick stew. The entire crust would become unstable. The first effect would be the cessation of all earthquakes. Instantly. The stresses building up along fault lines like the San Andreas would vanish, but that's the only quiet moment. Then, the rebounding begins. Rock that has been compressed for billions of years has a kind of elastic memory. It wants to spring back. All over the world, the continents would begin to rise. Not uniformly, but in a chaotic, fractured heaving. Mountain ranges, which were formed by the collision of plates and are held down by gravity, would begin to unzip. The Himalayas, the Andes, the Rockies, they would start to disintegrate as the rock, no longer pressed together, expands and fractures. Gigantic slabs of rock, the size of cities, would crack free and begin to float away from the planet's surface. But the crust is just the thin skin. Let's go deeper. The mantle, which makes up most of the Earth's volume, is solid rock. But over geological time, it can flow like a viscous fluid. It's hot and under tremendous pressure. Release the pressure, and you trigger a phenomenon akin to a massive planet-wide version of what happens when you open a champagne bottle. The decrease in pressure lowers the melting point of the rock. Solid mantle rock would spontaneously melt in vast regions. At the same time, the release of confining pressure would cause the entire mantle to expand, fracturing and becoming permeable. This brings us to the core. The Earth's core is divided into a solid inner core and a liquid outer core, both primarily made of iron and nickel. The pressure at the core is over 3.5 million times the atmospheric pressure at the surface. The existence of the solid inner core is entirely due to this incredible pressure, which keeps the iron solid despite temperatures exceeding 5,000 degrees Celsius. The moment you remove that pressure, you remove the very thing that is keeping the inner core solid. Instantly, the solid inner core would begin to liquefy. But it's not a calm melting. It's a catastrophic phase change, releasing an enormous amount of energy. Furthermore, the liquid outer core, now free of the immense weight of the planet above it, would no longer be contained. It would begin to expand violently. The entire core of the Earth would effectively turn into a bomb. The magnetic field generated by the churning convection of that liquid outer core would vanish in an instant. The Earth's protective shield against solar and cosmic radiation would be gone. But that's almost a footnote at this point, given the other events. So, the surface is breaking apart, the mantle is melting and expanding, and the core is undergoing a catastrophic phase change. The planet is quite literally coming apart at the seams. What you would see from your protected vantage point is the ground below you cracking into continent-sized plates, with glowing, red-hot mantle rock welling up in the fissures. These plates themselves would start to drift apart, not slowly over millions of years, but over hours and days. They would begin to rotate and tumble slowly in the void where the Earth used to be. The oceans. The oceans. All that water, covering 71% of the planet, was held in place by gravity. Without it, it is no longer bound to the surface. The oceans would simply detach from the seabed. It would be the most spectacular sight imaginable. Trillions of tons of water, forming a single, colossal, shimmering sphere, slowly pulling away from the disintegrating rock. It wouldn't be a neat sphere at first. It would be a chaotic, tumbling mass, swallowing the floating continents and city fragments, pulling in the atmosphere that hasn't yet escaped. Within this giant water planetoid, you'd see the remnants of ships, whales, submarines, and entire coral reefs, all trapped inside a liquid tomb. The water would quickly freeze on the outside due to the vacuum of space, forming a shell of ice. But the interior might remain liquid for a while due to pressure and residual heat. So, within a matter of hours, the Earth is no longer a planet. It is a rapidly expanding cloud of debris, continent-sized chunks of rock, a massive sphere of water and ice, and a dispersing cloud of atmospheric gases. The beautiful blue marble is now a chaotic ring of destruction, a new asteroid belt in the making. But we are not done, not by a long shot. We've only talked about Earth. Gravity was switched off everywhere. The repercussions echo throughout the entire solar system, the galaxy, and the universe itself. Let's start with our immediate neighborhood, the Moon. The Moon is in orbit around Earth. Why? Because Earth's gravity is constantly pulling the moon towards it, bending its path into a near circle. The moon is also constantly trying to fly off in a straight line due to its inertia. The balance between this inward pull and its tangential velocity is what keeps it in orbit. The moment gravity stops, the inward pull vanishes. The moon is now an object with a velocity of about 1 kilometer per second, and suddenly, nothing is pulling it off its straight line path. It would cease its orbit instantly and begin moving in a straight line, tangent to its former orbit. It would fly off into the solar system, a new rogue planetoid. The same is true for every single artificial satellite, from the International Space Station to GPS satellites. They all become independent, unguided projectiles, flying off on their own paths. The ISS, which was also experiencing microgravity because it was in free fall around the Earth, would now find itself in a true zero-G environment, and it too would fly off on a tangent. But the moon's departure is the least of our worries. Let's talk about the sun. The sun is a massive ball of plasma, 1,000,000 times more massive than the Earth. It exists because its own immense gravity is constantly pulling all its mass inward, creating the fantastic pressure and temperature at its core needed to sustain nuclear fusion. This gravity is fighting a constant battle against the outward pressure from the fusion reactions. It is a stable, balanced, and beautiful equilibrium that has lasted for billions of years. Switch off gravity. The moment you do, the entire reason for the sun's existence vanishes. The inward crush that was containing the stellar furnace stops. The balance is shattered. The outward pressure from the core, which has been held in check for eons, is now unopposed. The sun would not go out. It would explode. But it wouldn't be a supernova. Our sun isn't massive enough for that. It would be something different. A catastrophic, rapid disassembly. Without gravity to hold it together, the sun would simply expand outwards at an incredible rate. The pent-up energy from fusion, no longer constrained, would blow the entire star apart. In a matter of minutes, the sun would transform from a stable star into an expanding cloud of hot plasma, rapidly cooling and dissipating. From Earth's perspective, or the cloud that was Earth, the sky would turn blindingly white for a few moments as the last light from the disintegrating sun reached us, followed by permanent darkness as the plasma cloud expanded and thinned. The source of virtually all energy for our solar system would be gone. And what about the other planets? The same fate befalls them all. Jupiter, the gas giant, would simply puff away into nothingness, its gases no longer held together. Saturn's beautiful rings, which are made of orbiting ice and rock particles held in place by Saturn's gravity, would instantly disperse, the particles flying off in all directions. Every planet, asteroid, and comet in the solar system would undergo a similar dissolution. The solar system, a beautifully orchestrated clockwork of orbits for over 4.5 billion years, would cease to exist in an instant. It would become a diffuse, expanding cloud of dust, gas, and planetary debris, drifting through the interstellar void. But we must think bigger still. Gravity is not just the force that holds planets and stars together. It is the force that shapes the universe on the largest scales. It formed galaxies from the primordial gas after the Big Bang. The Milky Way galaxy, our home, is a collection of over 100 billion stars, all orbiting a common center of mass, held together by their mutual gravitational attraction. Switch off gravity, and the glue that holds the galaxy together vanishes. Every star in the Milky Way, including our now vanished sun, would stop its orbital dance. They would all fly off on straight-line paths, diverging from one another. the beautiful spiral structure would dissolve into a scattering of stars. The same would happen to every galaxy in the universe. Andromeda, the Triangulum galaxy, all of them. The universe would become a much more uniform and much lonelier place. Just stars and stellar debris all drifting apart. This has a profound implication for the ultimate fate of the universe. Cosmologists talk about the shape of the universe. Is there enough mass and gravity to eventually halt the expansion and cause a big crunch? Or will the expansion continue forever, leading to a heat death? By removing gravity, you are effectively removing the only force that could possibly counter the universe's expansion. You are ensuring that the Big Rip, or heat death scenario, is the only possible outcome. And you've accelerated it to an instantaneous event on a cosmic timescale. The large-scale structure of the universe, the cosmic web of filaments and voids defined by dark matter and gravity, would simply evaporate. Now, let's get really, really small. We've talked about planets and stars and galaxies, but gravity operates at all scales, right down to the subatomic. So, what happens at the quantum level? This is where physics gets very, very weird, and we have to tread carefully. In our everyday experience, the gravitational force between two individual atoms is so infinitesimally small that it is completely negligible. The other forces, the electromagnetic force, the strong nuclear force, and the weak nuclear force, are vastly stronger at small scales. They are what hold atoms and molecules together. So, if gravity stopped working, would a single hydrogen atom simply fly apart? Probably not. The electromagnetic force that binds the electron to the proton is about 10 to the 36 times stronger than the gravitational force between them. Switching off gravity would have no noticeable effect on the structure of an atom. Your body's atoms would remain intact. Molecules would stay together. The chair you were sitting on would still be a solid object, held together by electromagnetic bonds. However, there is a but. General relativity tells us that gravity is not a force in the traditional sense, but a curvature of space-time caused by mass and energy. When we say switch off gravity, are we saying that mass no longer curves space-time? This is a profound question. If mass no longer curves space-time, then the very stage upon which the universe plays out becomes flat and featureless in terms of mass-based curvature. This might not affect the other forces directly, but it fundamentally alters the geometry of the universe. It's a paradox that likely has no answer within our current understanding of physics, because you're essentially asking what happens if you remove one of the fundamental pillars of reality itself. For the sake of our thought experiment, let's assume that at the macroscopic level, the attractive force vanishes, but the microscopic integrity of matter remains. So you, your house, the earth, all stay together in the sense that their atoms don't fly apart, but they are no longer drawn towards each other. This leads to one last poignant consideration. What about life? Not just human life, but all life. Life on Earth evolved in a 1G environment. Our physiology is defined by it. Our bones are strong enough to support our weight against gravity. Our muscles are designed to move us against it. Our cardiovascular system uses gravity to help with blood flow. Without gravity, as astronauts on the ISS have shown us, bones decalcify, muscles atrophy, and fluids redistribute in the body. In a permanent zero-G world, human life would be impossible in the long term without artificial gravity. But in our scenario, there is no long term. The decompression of the atmosphere, the disintegration of the planet, the death of the sun. These are all civilization-ending, biosphere-ending events that happen in hours or days. Life, that beautiful, tenacious, and fragile phenomenon, would be extinguished from the earth almost instantly. The only possible survivors might be extremophile bacteria buried deep in rocks, and even they would be flash-frozen, irradiated, or blown apart as the earth disintegrated. So, there you have it. From a floating coffee cup to the dissolution of the cosmos, a chain of events so complete and so total that it leaves no stone unturned, because eventually there are no stones left to turn. It's a terrifying, humbling thought, isn't it? That something so quiet, so constant, so ordinary that we never even give it a second thought is the very thing holding our reality together. It's the hand that keeps the coffee cup on the table, the world beneath our feet, and the stars in their heavens. So, the next time you feel the solid ground under you, or watch a leaf flutter down from a tree, take a moment, appreciate the pull. That invisible, unwavering force is not just a law of physics. It's the anchor of our existence, the sculptor of our universe, and the silent, powerful reason why there is a down to look at and an up to dream about. Without it, there is only a silent, drifting end. Good night. Have a deep, calm sleep.